First start with thanking Axel for inviting me to talk here. Am I in the way or?
No, not yet.
Not yet. Where should I stand?
You're standing perfect. Just go
ahead. Okay. And my name is Astrobio07c, and I am a PhD student at the Stockholm University at the Department of Geology and Geochemistry. And the title of my talk is Detection of Biomarkers in Oil Using Toxins, and the implication then for earlier studies in Mars temperature. The project I'm working on is a cooperation between Stockholm University and SB Technical Research Institute of Sweden, which is situated in Borås. First I'm going to talk a little bit about biodiversity earlier, and as we heard yesterday, there's always a lot of controversy about any microfossil presented that's from the earliest, usually around 3.5 billion year old or something. And there's been this is where the thing I'm studying, biomarkers, can provide additional information on the biodiversity of early Earth. And when I'm talking about early Earth, it's mostly Archean and Proterozoic times, which is about 2 to 3 billion years. Oh, nice. What is then biomarkers? Well, biomarkers are organic molecules that can be traced to a specific organism, and in the right corner here you have one type of biomarker which is called cholesterol, and many of these biomarkers are remnants of lipids in membranes. So they're basically, cholesterol here is basically the breakdown structure of a lipid called cholesterol, which we all recognize actually. And what's happened is the cholesterol has lost its functional groups here, and but the main, basic carbon skeleton is still left, so it's pretty easily identified when you find it then in geological records. Examples of biomarkers are cholestein's type of styrene, which you see, and then again on the left, and then we have also hopanes. And here you can, for example, styrenes, they come from eukaryotes, while the other hopanes is basically doing the same thing as styrenes are doing for eukaryotes, but they're doing it for bacteria instead. So if you find hopanes, you know you have bacteria, but if you find styrenes, you know that you have eukaryotes.
I have a question there. I suppose that most of these rings are carbon.
Yeah. It's basically just carbon and hydrogen.
But these extensions there, is there anything else than carbon?
No, it's just carbon and hydrogen. Hydrogen, of course.
Yeah.
So the saturated, compounds except for it. Another additional advantage of biomarkers, of course, in the geological record is that they're extremely stable. They have been found in 2.7 billion year old bitumens in Western Australia by Broxenol. However, there has been questions raised about these 2.7 billion year old biomarkers, and that is they really real, or are they really 2.7, or they're just contamination, just maybe the researcher or something putting their basically fingers on them. So therefore there's a need for new kind of samples where the contamination risk has been minimized when you're looking for these. And this is also, of course, true if you would like to bring home samples from Mars. You need really to control that you're not analyzing your own fingerprints and actually something from Mars. And example we have here, the famous meteorite Allen Hill. One type of samples that could provide this is so-called fluid inclusions. Fluid inclusions are defects in minerals where oil, water, or gas has been trapped, or all of the above. You see some of this on the... You have something to point to?
Yes. Yes, it's just fine.
You see them here? These are containing oil. That's why you get the slightly brownish yellowish color here. And this is actually a gas bubble inside trapped. And you could call fluid inclusions kind of time capsules, as the fluid in the inclusion is protected from any changes in the surrounding environment after the inclusion has been closed off and until it's opened again. Fluid inclusions are small. They're a couple of micrometers. There are some that are maybe 30 microns you can find also. The mass content is maybe femtogram to nanogram. This means if you want to analyze actually the chemical content of the inclusion, and you need to open a lot of the inclusions at the same time to get enough material if you want to analyze it with the standard technique, which is gas chromatography, mass spectrometry, GCMS. The problem with using this technique is that usually in the same rock or even in the same crystal, there can be different generation of inclusions. And with different generations, I mean, and between different generations, there could be, one could have been formed first and the other one could have formed millions of years later. So you get a pretty crude picture of what you actually, if you open all of them at the same time and analyze them.
But does it matter? I mean, a million there.
Oh, well, it could be half a billion. I'm saying, like, it could be many hundreds of millions of years between. And the content, actual chemical content, could have changed quite a lot in the meanwhile. And therefore, it would be advantageous to analyze single fluid inclusions. How about biomarkers then in fluid inclusions? Well, biomarker has been found in 2.5 billion year old oil-bearing fluid inclusions. I should probably point out that I'm talking here now only about oil-bearing fluid inclusions, because that's where you find the biomarkers. Usually in oil, then biomarkers are in very low concentration, just ppm. So if you would like to analyze biomarkers in single fluid inclusions, you need an extremely sensitive techniques. And this is where TOF-SIMS comes in. TOF-SIMS stands for time of flight secondary ion mass spectrometry. And what you're basically doing is that you're bombarding a surface, and it is the surface, as TOF-SIMS is a surface sensitive technique. It's the surface you're going to analyze. So you're bombarding the surface with the primary ions, and in the process, secondary ions or particles are generated. In my project, I used a so-called polyatomic ion source, which are the new kind of sources coming. First, before it was more mono ions used, and if you're using this kind of polyatomic, you can reach the sensitivity. If you have 10,000 molecules within the analyzed area, you will detect the molecule you're looking for. This stands for organic molecules. After you generated your secondary ions, they will be accelerated into this time-of-flight mass spectrometer. And what basically happens is that you accelerate you give all the ions the same energy, and as they have different mass, they will reach the detector at different times. So you get a separation in time, and then you can recalculate it into mass then again, and you will get a mass spectrum. What then have I done? Well, I haven't really yet, or I've started, but the first thing I did was actually to see if I could detect biomarkers just in oil, not in oily fluid inclusions, but just any oil. And I started by just analyzing pure biomarkers like stirrings, and this is the first time these kind of, at least stirrings is the first time someone analyzed the kind of in TOF-SIMS, just to see how the mass spectrum, so we have a reference mass spectrum. Then we also analyzed oils, and we analyzed both the fractionated and non-fractionated oil. And fractionated just means that you remove all the polar components in the oil and just keep the non-polar components where the biomarkers is found to make it slightly easier. And then we also analyzed, and non-fractionated just means you have the whole oil still. And we analyzed.
Was that crude oil or?
It's crude oil, natural, which you can pump up out of any well, basically. And then I analyzed it both with TOF-SIMS and then GCMS, as this is the standard technique for analyzing oil. And I also started doing some consultation studies. And this is the result from one of the pure biomarkers. This is then a styrene, alpha 20R cholesterol. And what you see here is this molecule has a mass of 372. And the strongest peaks, except for below 100, is basically the molecular ion, which lost one hydrogen, the 371. And we also have all of these other here are basically fragment peaks when the molecule is fragmented. And one important is 217 because it's usually used as a diagnostic peak for the styrenes in GCMS. And this is the breakage then on the pentarene here. And then this is for our whole pain then. And this is then a 17 beta 20 alpha whole pain. And the mass of this one is 412. And once again, you see the same pattern that one of the strongest peaks is the molecular ion, which lost one hydrogen here at 411. And then we also have, here we have stronger fragment peaks. One interesting is 191, which is the diagnostic peak for whole pains and GCMS. And which here is the breakage of this, one of the sites of the hexane. Then if we move on to the results from the oils, and this is oil from the Monterey region in California. And what we just wanted to do with the GCMS is to see that we actually have the whole pains and styrenes we're looking for in the top sin. And this is this is the whole chromatograph, so this part here contains the styrene and the whole pain.
What is UCM?
It stands for unresolved complex mixture. The GCMS is not able to separate all the components, so some co-load. And usually the more biodegraded the oil is, the bigger this hump gets, because it's basically breaking down to a lot of small, it's just co-loading everything at the same time.
But don't you have mass resolution enough to resolve this? Or?
It's not the mass resolution, this is a chromatogram, so it's just showing the...
Oh, this is not the chromatograph?
No, this is just the GCMS spectrum.
Okay.
So this is the chromatograph where you see after the GC color. Here is the toxin spectrum. And what I should tell you is that this is the non-fractionated, the fractionated oil. So we removed a lot of the polar components. And this is true for the GCMS, it's also just a fractionated oil, as you can't analyze the whole oil in GCMS in the same. So here we see the 371, which we saw in the cholesterol spectra. We also see these 385 and 399, which is the styrenes with the additional methyl groups. And you also see 411, 455, 439, which is also then a whole pain series in the same spirit. And well, there are not a lot of other peaks, of course, but it's not a lot of other things in this oil. And then we also have the fragment peaks in this spectra. We have the 191, the diagnostic peak for whole pain, and also 217 diagnostic peaks for styrene. All of these marked here are fragment peaks for cholesterol and whole pains. Then I also wanted to see if I could see the peak in the non-fractionated oil, because if you're analyzing oil in an inclusion, it will be, of course, non-fractionated. And this is the fractionated oil again. I'm just focusing on this 371 peak. And you do see it again in this is the same peak in the non-fractionated oil.
I wonder, the wiggles in this, I'm very familiar with this type of spectrum. Is that noise or is it other structures which is not fully resolved?
It's noise. I mean, this is one peak, this is one peak, and this is one peak. And this is also one peak.
So the big peak in the lower diagram are polar compounds?
Yeah, so it's basically being cut off here.
What kind of polar compounds?
Or they're not very, I would say that this is probably some kind of aromaticized stirring. So it's maybe one or two of the rings has been aromatized, which means that they lose hydrogens, which means that this peak is more moving towards the integer. And then when you add like oxygen and stuff, you would move even lower.
Does it mean that it's destructed by the process, or is it?
Sorry?
I mean, it's a destructive experiment you're doing, but the point, as I understand it, is that some of the big molecules can still be detected, and then it's a destruction.
Well, there's
spectrum.
destruction, but this one is not destructed very much. It's just lost one hydrogen.
Yes.
But in the lower part, it's fragmented up. Yes.
But in the lower curve there, so is it still?
Oh, you mean this one?
Yes.
This is a whole molecule also.
Okay.
So it's not destructed. It's just another. I mean, there's I don't know how many components in an oil. It's a lot of different components. So it's surprising that you find a lot of different peaks in the spectrum. And this is another oil. We didn't just analyze one oil, we analyzed several oils, and this is oil from the Cillian. And here it's stronger than the peak from the string. So the conclusion is that the biomarkers produce strong and highly molecular specific spectra in toxins, and that it is possible to detect biomarkers in oils using toxins, especially in fractionated, but also in non-fractionated oil, which means that we could start actually analyzing biomarkers in single oil-bearing fluid inclusions. For this, we probably need to modify the toxins instrument, and also develop interpretation schemes for toxin spectra of oils. And then we also going to merge, as we develop the method, we'll probably also continue analyzing. We will continue then analyze oil-bearing fluid inclusions from earlier, and we do already have the access to these types of samples, which is around 2 to 3 billion-year-old samples. And last, I want to thank my supervisors, Thomas Holt and Luca Lausman, for the help. We also want to thank Parker Thiel, which helped us, which is a German professor, which helped us with the GCMS analysis. And also we got funding from the Swedish Research Council and Swedish Spaceport. And last but not least, Fred, who's been listening today. Thank you.
Thank you. Questions?
Yes.
This 12 SIMS, is that the one located at the Natural History Museum?
No, that's a Nord SIMS, and it's a nano SIMS.
Okay, so the one you're using is located where?
In Borås, at this SB technical.
Okay.
It's the old SB. It's the oldest.
We call it
provningsanstalt. Yes.
But I had a second question.
Yeah.
This using bismuth, this bismuth molecule, I guess that this is by trial and error that you find out what type of primary ion you should be on the surface.
Yeah, it's a development. Before they used more the gallium, as the mono ion, but then they started experimenting with this type of polyatomic. In the instrument I'm using, it's just this is the source that's mounted, so of course you could change it.
Well, for me, it seems to be a very good progress in getting in analyzing a very small sample.
Yeah.
The only concern, in my view, is that it's destructive, and so the alternative methods like fluorescent spectra and such things, I guess that these have been tried.
Fluorescence, then you have to open it and then add it, but
not necessarily. I guess that the inclusion.
Oh, you mean fluorescing, but you will only get, you have aromats here, basically. You don't get.
You can't tell anyone.
No, all these infrared, and the problem is that you don't get out that much. information. I would say that it's probably nice to have some combined. You can have a combined. I mean, you can have some infrared and Raman and stuff, but you get limited information out of them because you just get the functional groups, and so it's extremely hard to identify something in such a complex mixture as the normal.
Well, you didn't tell us how you open up the conclusions. You haven't tried it yet, or?
Well, we have.
Yeah.
And it's worked, but it's kind of, we don't want to talk too much, or
okay.
it's a secret. René?
This was very interesting, I think. And you have been concentrating or focusing on oil,
Yeah.
on crude oil. I guess there is very little of this stuff around on Mars, for instance.
Yeah.
Do you find these molecules in certain soil as well?
Sorry.
In normal soil, if you just pick up a
Yeah.
piece of dirt, would you see the same signature?
I think so. I mean, you can see them at least in oil shales. I'm not too sure actually if you find them in, I don't know, I think actually you can find them in oil because there's a big contamination. I mean, there are also always worries about contamination, so you can find them if you find in certain oils, in certain soils.
But how about doing such an experiment on Titan? Would that be something one would like to try?
Well, first then you have to miniaturize the toxins.
Yeah. That not
You can go and get it, collect the stuff and come back.
Yeah, that's where we are focusing more on sample return because the toxins in itself is pretty big.
Yeah, it has
It's
to be
a big, it's a big.
Yeah.
I mean, even though I've seen actually like attempts to in these comets where they actually try to miniaturize some kind of TOF MS and some kind of SIMS. I don't know if it's exactly a TOF SIMS, but something similar. And this is, I guess, more for analyzing like simpler. I mean, they're sending like ion traps and ion trap mass specs and stuff. So, but I mean, you have the primary ions and you need the bloods. So this is, and it's, I mean, usually you get better spectrum the bigger the longer the time of flight is. So, so I guess that's slightly hard to minimize that. But I think they will try to minimize this instrument, I'm sure.
But your next step now is to try to attack these small enclosures.
Yeah, that's what we're working on now. So as I was saying, we actually managed to. So I mean, and it's not as destructive as I mean, these are. I mean, this is basically the whole molecule from a simple one.
That's a good thing.
Yeah. And
it's very promising.
It's, I mean, compared to like nanosims, it's extremely not. Nanosims, you just see the elements basically. So here you actually, this is one of the good things with toxins, that you can actually see big organic molecules. And I don't know, you can see up to like, at least you can see. I think they've seen up to like, I don't know, 5,000 AUMs, and these are very, very small compared. So they've been analyzing much bigger lipids and stuff in this one. Another big advantage with this one is that you get an imaging. You can get imaging, so you can actually localize where your organic molecules are.
And you can direct your ion beam onto the small enclosure.
Yeah.
And you can focus it good enough.
Yeah. And I don't remember what the. I mean, as they do imaging, you need a pretty good spatial resolution anyway on the beam. So, otherwise you can't do any imaging. So, but I mean, the image, a couple of micrometer stuff. So, it depends a little bit on the ion beam and stuff. Yeah.
Good luck.
Oh, thank you. No more questions?
So, thanks.
Next speaker is Mats. talking about slightly less massive.
Yes, slightly massive, less massive. So this is really the simplest polyatomic ion there is, and it probably could be as a bit of a surprise to you that the recombination of this ion with electrons could pose any problems in terms of measuring this rate or calculating. H3 plus plays a very important role in astrophysics, and in 2000 there was a Royal Society discussion meeting on this, only on this ion, spectroscopy, reaction dynamics, spectroscopy, astrophysics, and so on. And at this meeting the recombination of H3 plus was discussed extensively. And then 6 years later there was another Royal Society discussion meeting on this ion. And there was a special issue in philosophical transactions only dealing with H3 plus. I'm a bit proud here because I have a very short article, 2 pages, but it's based on my after-dinner speech. So it's the only time I got to publish my after-dinner speech. Yes, that was me.
What?
No. Just some historical notes. We heard about mass spectrometry in Celia's talk, and the very first development of mass spectrometry was by J.A. Thomson. And when he first set up his mass spectrometry, he detected an ion with mass 3 and concluded that was the H3 plus molecule. Later on, when the deuteron was discovered, he was for a while uncertain whether his discovery was correct. He thought maybe he had discovered HD plus. But later on it turned out to be correct. It was H3 plus he had discovered. It took a very long time, though, before a high-resolution spectrum was observed. And the reason is that H3 plus does not have a rotation spectrum. It does not have an electronic spectrum in the visible region. So the only route to detect the spectrum is through the infrared. And the sense that it's extremely difficult to do infrared spectroscopy on molecular ions. So it was a long development by Oka to where he used the state-of-the-art at that time lasers to detect an absorption spectrum of H3 plus. And then came a series of discoveries of H3 plus in astrophysics. The first one was discovered in the ionosphere of Jupiter. Later on in dark molecular clouds by Oka, and then a few years later in diffuse clouds. This was quite surprising at the time that it could be discovered in diffuse clouds. And then it has now been observed also towards the galactic center. It is formed in interstellar clouds by first ionization of H2, which takes on the average 1 billion years. And H2 is ionized by the cosmic ionization rate. And I'm coming back to this cosmic ionization rate at the end of my talk because it has an infinite connection to what we have done. The next step, though, is much quicker. As you can see, it's only about 2 months for the reaction of H2 plus with H2 to form H3 plus H. And that's when I talk about this to the student, I ask them, what is the rate limiting step here, the reaction? And of course, H3 plus then is the key initiator of a number of reactions, building up more complex molecules. For example, here you see how H3 plus can react with oxygen. The reason why H3 plus is so reactive is it tends to donate a proton to essentially anything it collides with. So it starts the reactions here, OH plus, and then you have a sequence of bimolecular reactions leading up to H3O plus, and then recombination with electrons forming water or OH. And the same way you can see here more complex reactions leading up to, for example, here ethanol, for example. So this is a reason why H3 plus is so important, because it really starts the chemical reaction networks. Of course, it's destroyed by reactions with neutrals, primarily in dark clouds. In diffuse clouds, the primary destruction route is by electrons. And this would seem like a very simple reaction to study. And of course, it has been studied over many years, but there has been big controversies as to how quick this reaction is. I should say that the recombination of H3 plus with electrons can be either to break up into 3 hydrogen atoms or a hydrogen atom and a hydrogen molecule. This is a tricky thing to sort out, but we have done this in experiments in cryo-ring. I don't have the time to go into how we do this, but I think it was a very elegant experiment at the time that when we measured this. So this one explains the problems with the recombinations. On this axis you have the recombination rate constant in cubic centimeter per second, and ranging from 10 to the minus 7, which is a quite, shall we say, ordinary rate constant for electrons recombining with molecular ions. It is a very fast process. On this axis you have the year when the particular laboratory measurement was done. And as you can see, it started off here in the early 1970s with quite ordinary, shall we say, expected results. But then came a period when the rate constant dropped, and dropped down to very low values. And these values became dominant in the models for diffuse cloud chemistry. And there is an influential paper by Van Dishoek and Black in the 1980s where they adopt these low values. That was measured by a Birmingham group, David Smith and Nigel Adams. What is surprising is that they never really published these results in any detail. It's only in conference proceedings, and you cannot, it's not possible to really look at their data in any detail. And so it's, in retrospect, it's very surprising how such papers could have such an influence on the astrophysics community, I think. As you can see, the result went up again, and when cryo just came into operation, we did the first experiment and measured the rather high rate, which led to a long controversy with David Smith. He finally accepted that these results were wrong, and that it had to be raised quite a lot. But that was a long battle. And, the problem here, I mean, you could probably think that H3 plus is such a simple molecule, so why, if there are problems with the experiment, why not calculate this? I mean, already 20 years ago, you could calculate the spectroscopy of H3 plus almost to an accuracy of experiments. So why not calculate it instead? Well, it turns out that it's extremely difficult to do these calculations, and it's only during the, say, past 5 years that people have developed techniques now that allows calculations that seems to be quite accurate. And this would be a technical talk in itself to discuss the calculations. Just let you know that it's extremely difficult. The state of the art in the year 2000 was gave a rate constant of 10 to the minus 9. So you can see that theory was not really very helpful in guiding experimentalists here. I mean, this one fell sort of in a no man's land, where either higher than this and lower than this, 5 orders of magnitude. So I mean, we're not talking about, we have a logarithmic scale on this axis. Oops. This is a bit messy, but it tries to explain why this is, shall we say, the mid-1980s picture of H3 plus recombination. You have the ion ground state here, and you have a neutral state here. So in the usual framework of recombination, you would expect the ion residing, say, in this level here, to capture an electron, and then the molecule dissociate along this resonance state. The problem here for recombination would be that if you're in this level, it's rather a long way tunneled through to this resonance state, and this made many people believe that recombination of H3+ in the lowest vibrational level would be very slow, whereas recombination in vibration excited levels could be very fast. And this could possibly explain the big variation in experimental results. So the key to do this experiment has really been to control or to have some understanding of the quantum states that are populated in the H2+ ion. Here you see the structure of the ion. It's a perfect triangle, an equilateral triangle, each side the same length. There are symmetric vibration modes and there are antisymmetric vibration modes. And if you plot them in a diagram like this, you see the zero level here, and then the first antisymmetric stretch here, first symmetric stretch, and then you can add on and you come up to, say, 10,000 wave numbers, and the molecule becomes so floppy so that it can become linear. All these levels can now be calculated with spectroscopic accuracy. But then we're talking about structural calculations, not dynamic calculations, which is the case in recombination. Let's zoom in on the lowest transition, and you will see the rotational structure here. So that these are the J = 1 levels, with the G quantum number either 0 or 1, which is also labeled ortho or para. This has to do with the characteristics, which is depending on how the spins in the three protons are aligned. And in the stellar conditions, only these two levels are populated, except for rather warm H3+ towards the galactic center, where they have now recently detected J = 3, which requires more than 360 Kelvin to populate. These levels are very long-lived, so they would, if you populate J = 3, you will stay there for a very long time. But under normal, say, interstellar cloud conditions, these are the only two levels that are populated. And of course, if you have a light source, you can then absorb from down here up to here, to these levels, and this is precisely how H3+ was observed in diffuse clouds about 10 years ago. So you have a diffuse cloud, you have some background stars shining through the cloud, and here you see the fingerprint of H3+, the two R lines, the R11 and R10 lines, occurring at about 3.7 micrometer. And this was made possible because of the increased sensitivity of infrared spectroscopy. We have an expert sitting here, front row on this. So here is the device that we have been using to study H3+ recombination. And once again, it may surprise you that this is a fairly big machine for studying a process where you really want to measure low energy collisions between electrons and ions. So this is 52 meters in circumference, and it's a megavolt machine. So you create ions here, you inject them, accelerate them to mega electron volts, and then merge the ion beam with an electron beam over a section of roughly 1 meter. And there's an acceleration system here in the machine. This would be called a synchrotron. And it's the same working principle as a light source, synchrotron radiation light source. But we only use ions and not electrons, which means that there is no radiation, of course, coming out from it. Now we'll see if this animation works. So this is the electron beam now being merged with the ion beam. So you see the ion beam is here. The electron beam is deflected into this section, merged, and then the electron beam is deflected off. The ion beam continues, but neutral particles are separated from the ions. So the neutral particles, they just fly out of the machine. And we can measure them by just putting a detector here and counting the number of particles coming out. And then by changing the relative velocity between ions and electrons, we can very carefully regulate the collision energy. And we can measure them as a function of collision energy over a rather large dynamic range, as you will see. The situation of H3 plus as of 2001 was the following. I mentioned that we had measured in triring in the 1990s. We measured the rate constant of 1.1. This was confirmed by measurements in the Astrid storage ring in Aarhus. See, we obtained basically the same result. There were new flowing afterglow experiments. This is a different type of experiments really coming from the ion chemistry community, and this gave a very low rate constant. So we had a clear discrepancy here, and I already mentioned the theoretical calculations which really supported this low rate constant. So this was the problem as of, say, 2001, and of course then you start to worry about possible systematic errors in your experiment, and one such possibility could be a contamination of vibrationally excited levels in the experiment. And but then in 2002 there was a publication from a German group also using a storage ring, where they had taken out part of the beam from the ring and sent it through a thin foil, doing so-called Coulomb explosion experiments. You send the ions through this thin foil and it explodes, and you can take a picture of the 3 nuclei. And by analyzing this picture, you get information about the vibrational modes. And what they could see was that if you stored the ions for more than 2 seconds, the picture then never changed again. So that after 2 seconds, one could draw the conclusion that all the ions had decayed down to be equal 0. So there would be no contamination of vibrationally excited levels. So that could be ruled out. But there was another problem, and another serious problem, and that was that the ion sources that we used produced rotationally hot ions. And these excitations are much more difficult to get rid of than the vibrational excitations. The vibrational excitations, we store the ions for a few seconds and they just relax down to the lowest level. This doesn't happen for the rotational levels. If you produce them highly excited rotational levels, they remain, some of them remain there for lifetimes that are much longer than we could ever achieve in the storage ring. So, and it also turned out that the rate constant was affected by the rotational temperature. So here we had a problem. If we wanted to do something that was of relevance for interstellar chemistry, we had to address the problem of the rotational excitations. So that was the next step. And the strategy we decided to do, and this came out of a visit. I spent a few months in Berkeley and had discussions with people that having a lot of experience from H3 plus ions spectroscopy. So we decided to try to build an ion source that could deliver cold H3 plus ions, populating only these 2 levels that are populated in the stellar clouds. So we built a pinhole discharge ion source in Rick Sakeley's group at Berkeley, and then characterized this source by so-called infrared cavity ring down spectrometry. This is a characterization that you could not do here in Stockholm because we don't have this machinery for doing infrared cavity ring down, but they had it at Berkeley, so this was a key point. And then we shipped the source to Stockholm. We connected it to the tri-ring. We did some test experiment. It seemed to work fairly well, but we needed to do some modifications of the source. So we sent it back to Berkeley again and did further development on it, characterized it with the infrared spectrometer, and then we shipped it back to Stockholm for the final crucial experiment. And let me show you how this works. So we have H2 as feed gas, and we have the solenoid valve which opens with a frequency which is adjusted to the injection frequency into the storage ring. And there is a system of electrodes here. So you have this metal flange on ground, and then you put this metal ring here on close to 1 kilovolt. So when this one opens, the high pressure gas, this is at 2 atmosphere feed gas, it expands out through this very narrow hole, which is maybe only 0.5 millimeter in diameter. And when the gas expands out here, there will be breakdown in the electric field here, so that there is a discharge. And in this discharge, we get ion molecule reactions, so forming H3+. But in the very close to this orifice here, there will still be collisions, and this is an adiabatic expansion. So you get adiabatic expansion where you cool down the translational and the rotational degrees of freedom, and you create cold H2+ ions. So when we characterized this source at Berkeley, what we did then was to shine a laser, infrared laser, through here. And cavity ring down spectroscopy is a very sensitive technique for detecting direct absorption. And this is the system at Berkeley. So you start with visible photons. You take it into a so-called Raman shifter, which is a long cylinder with D2 deuterium, and so where you then shift the visible light into the infrared and take it down here, and then send it through two mirrors, high reflectivity mirrors, and the photon pulse will bunch back and forth here. But if there is something absorbing, the lifetime of this photon bunch will decrease. So this means that if the laser is at resonance with an absorption line, for example from H3+, then the decay time of this pulse will be shorter than if there is no resonance. And you spill out a little bit of the photons here and detect them. So this is a very highly sensitive technique for measuring absorption. And this is an absorption spectrum that we recorded with this ion source. So you see the two lines, the R11 line and the R10 line. And this shows you an absorption spectrum taken towards the diffuse cloud, which is located towards Zeta Persei. So what you can see here is that we managed to really emulate the relation between the two absorption lines in the interstellar cloud and obtain roughly the same relative intensity. So this convinced us that we had been able to produce H3+ in rotationally only two quantum states. We don't produce vibrationally cold ions in this source, but that is not so important because we know that if we just let them circulate for a while in the ring, they will relax vibrationally. So that's not a concern, it's really rotation which was the problem. But we think we solved this problem, and we connected it to driving, and we did this measured the recombination rate as a function of relative velocity between electrons and ions. And as you can see, we have quite a large dynamic range here in collision energies. We can go up to tens of electron volts down to less than milli-electron volts. And we recorded this curve. And we obtained after then, well, there is some data reduction, of course, you have to do on a curve like this. You have to transform it to a thermal rate constant. If we transform our results to a thermal rate constant, we obtain something which is here, clearly lower than we had before. So that shows that where we had a much higher rotation temperature. So this shows that the rotation increases the rate constant, just that we had expected. But you can also see that there is no way that we, even with only two rotational levels populated, could come down to the theory of the 2000. Fortunately, there was also, in parallel with our experimental work, there was a theoretical development. And this is the key paper that came from Gilla, Chris Green's group, where they found a new mechanism for the destruction of H3+ by electrons. And there was also some news about this called the chemistry of interstellar ions. So this was really the breakthrough. And then, of course, this was followed by several long papers in Fist of Letters, a short one, and then a long paper in PRA. And when they deduced the thermal rate constant, you can see that they obtained something which was more or less coinciding with our experimental results. So I think this finally convinced the whole community that this problem were more or less solved. I mean, we had our experiment with few quantum states, we had theory now coinciding, and then 1 year later came an experiment in Germany where they had used a completely different type of ion source, but also producing cold ions. and the result was in absolutely perfect agreement with our experiment. So we felt very convinced by this. And this made it possible then to address the question of the presence of H3 plus in diffuse clouds, because I told you that this came as a little bit of a surprise that it could be observed. And because you would expect, if the rate constant of 10 to minus 7 or less, or a little bit less than that, would be the prevailing in the stellar clouds, you would expect H3 plus to be destroyed so quickly, so it would be difficult to observe. And the density of H3 plus can, in a simple model, be related to the column density divided by the length of the cloud, and this can then be related to the cosmic ionization rate, H2 number density, electron density, and the recombination rate constant. And this we had measured then as I told you, and then we studied one cloud where the electron density had also been measured, which means, and this one can be estimated. So we had 3 out of 4 components here, and of course you can measure the column density and the number density. So the only remaining factor then was the cosmic ionization rate. And when we did this exercise, we found, combining our recombination rate constant at 23 Kelvin, which is this number, the rate constant increases with the electron temperature. So the number I showed you previously was 300 K, but at 23 K, the rate constant is more than 2 10 to the minus 7. And we had the electron density estimated from measurements of the carbon plus, which is the atom with the lowest ionization potential. And this gave a cosmic ionization rate of 1.2 10 to the minus 15 per second. And this value, as you can see, is much higher than the accepted canonical value for dark clouds, which is about 3 10 to the minus 17. I think in the beginning it was not so accepted that this could be the case. I remember I presented this at the conference just after we had done these measurements, and Dalgarno, he was rather skeptical about our results. But then I read now, quite recently, he published a paper in Proceedings of the National Academy of Sciences, and addressing the question of the cosmic ionization rate, and there he seems to have completely accepted that it could be high in diffuse clouds. So that was quite nice to see. So I am here with just acknowledgement of because this has been quite a long work, collaboration over quite a number of years, and including people in astronomy and a group in Berkeley, collaboration in Poland, and the groups in Stockholm, and supported by a number of funding agencies. So I stop there. Thank you.
I want to make a comment. This was a really nice result, I would say.
Shocking also.
Sorry?
Shocking also, I mean.
Shocking. I was immediately thinking of, we had enormous problems during the write-up of Ben-Glashan's thesis and one of the papers. In one of the regions, we encountered enormous problems with the OH and water abundance. The only way to fix the relative thing was to increase at least locally, the cosmic ionization rate. Yes. And we were sort of hand-wavingly referring to X-ray sources that might be there, but it didn't really give us. But this rate was exactly, essentially, we got a lower limit of 10 to the minus 16, which was not accepted. And that's, as you said, John Black is still waving with 3 times 10 to the minus 17.
Yes. And there are now discussions about why it could be different with diffuse and dark clouds. And I mean, we speculated that it may be that there is a low energy tail in the ionization rate, which has no problem to make it through a diffuse cloud, but which is blocked in a dark cloud. So we thought that could be one possibility. But I've seen that there are coming papers now addressing this question. And I mean, Dalgarno had his own model, which trying to explain H3 plus without increasing the ionization rate. And I remember how this was addressed in London in 2000, and see John Black and Evin van Dishop, they didn't believe this at all.
Do they do that now?
No, I think he left his, he had some other big clumps.
Yeah.
No, I think he's not using that at the moment. So.
Because we have a big problem with the HCO plus balance, which according to their models is we measure 10 times more than their models predict, and that will also be directly coupled to the ionization rate.
So I think this is on the right track.
Are you aware of is somebody pursuing observations of that kind?
Of what kind, you mean?
Of H2 plus?
I mean, Oka is constantly asking for observation times to look for it, but he's now, I think, more interested in the galactic center, trying to understand why you can see support. Yes, H2 plus at 300, more than 300K. Hard to understand.
I mean, in protostellar disks, we are of course extremely close to the situation where we either may or may not have a dead zone at 1 AU distance from the Sun. And with this revised cosmic ionization rate, cosmic ray ionization rate, that value may also completely change, and things may be much better ionized, and we don't have a dead zone.
Possibly, I don't know that.
What do you think? I mean, that's it's the same, exactly the same problem. There's no difference between a protostellar disk and a dark cloud, right? And I think, I mean, I've never heard, actually, somehow I've been living perhaps too much in the past, but I mean, obviously the 10⁻⁷ is all I know of.
Yes. No, that's the canonical number, so, and it's been assumed to be the same.
And so a lot of history needs to be rewritten, not history, but a lot of science needs to be redone now, of course.
Because under pure polar diffusion.
Yeah.
The time scales and
exactly.
Directly. Bye.
I was surprised when we did this. I thought that there were different ways of measuring the ionization rate, but then they told me that probably the best way is to do this through the chemistry
and by the way, yes, the destruction rate. Is this I mean, in order to have any ionization in a protostellar disk, do you think the prominent avenue is indeed always via H3 plus, or are there other ways which could be more important to ionize neutral hydrogen?
Well, I think, neutral H2, I think is usually ionized by the cosmic ionization.
Yes, but I mean, you are here calculating H3 plus rate.
But that one will, anything neutral will collide with the proton.
Yes.
That's clear, because it has such a low proton affinity, so it's really, in chemistry language, I guess you would call it an acid.
Yeah, but I guess that your question can be put differently. If you have a protostellar disk and irradiate it with charged particles, what is the cross section of H2 compared to other constituents like the H2O and such things that you can find in the disk?
Yeah, but H2 is so dominant.
Yeah, it is. So there is no question about it.
Mm-hmm.
So it's only at later stages when the H2 is sort of disappearing.
Mm-hmm.
Thank you.
Wow, amazing.
I just went up here, I didn't wait for you to say anything.
Okay, welcome.
Well, thank you for the nice introduction. And thank you, Axel.
Pleasure. Thank you for accepting.
So, thank you, of course, for a Dane. It's an interesting experience that Nordita has moved with me up here. I'm just waiting for Carlsberg and the Little Mermaid to follow, then I'll feel okay, I had the problem. I was ill the last couple of days, so that's why I was not here yesterday, and also it's the reason why I didn't really go through with what I had intended. I've been giving talks about the Desiree project several times, and now I wanted to do it completely different. So I started out doing that, and then I didn't finish it. So this will be somewhere in between an old and a new version of this, and I hope I'll make it to the end somehow. So what I'll be talking about is the Desiree project, and the Desiree is an acronym for Double Electrostatic Ion Ring Experiment. And this picture is of the Desiree. It's not a pinball machine, and you see two electrostatic rings in one vacuum chamber, and I removed the lid so that you could actually see something. And the idea is to store two ion beams of opposite charges and let them interact with each other to study their reactions. And I claimed in the title of this talk that I consider it as a tool for interstellar ion chemistry. And this is maybe the new part. First, it's important to prove to you that this works, so we made a movie of it. We have two ion sources. One ion beam is stored in one ring. So these are all just electrostatic deflectors and lenses skewing the charged particles on closed orbits. And we can store a beam like this. And then we have a separate injector where we load in an ion beam to the other ring. This is then a beam of opposite charges. So first was positive ions, and we have anions from the other one. And then over this section, the two beams overlap, and if we have some interaction, for example, one electron is taken from the negative ion to the positive, we form two neutrals that we can then detect. So this is the very fast description of the experiment that we plan to do. So this is where we start. We are back in the interstellar medium as in the previous talk. This is this so-called ghost head nebula. And I'm a week late maybe, but I couldn't resist. And here's an example of a dense molecular cloud defined by the astronomer cycle. I'm not saying something wrong now, simply by a cloud which is dense enough that you don't see any stars, any starlight from behind. And in these molecular clouds, one can of course ask what are the molecules that can be found in these regions. And there is a nice list of such of these molecules that can be found on the internet. I have a connection here, and it goes from the simplest you can think of course H2 is the dominating, but there are today 151 different molecular species that are detected in space. Some with more confidence than others maybe, but if we go through the list here, I'm not going to go through all of it. You find, of course, simple stuff as methane and water. And interestingly, you find also more complex molecules. Like, for example, this important one, ethanol. No, I'm always doing the same stuff. And this list even claims that you can find glycine. Now, most of these molecules are neutral molecules. There are also positive ions, and since very recent, also a few negative ions. I don't know if you see this text here, but I'll come back to this in a moment.
Is this in order chronological?
The order here is just by mass.
But just by
Yeah,
mass, not
yeah.
when they will be. Okay.
So, how are these molecules formed? This was addressed a little bit already in the previous talk. And then the sort of astrobiology aspect on this. How big and complicated, complex molecules can we form in this way? How far can we get towards molecules or their precursors in the stellar medium? And, well, I'll skip that one. So, we're back now to the favorite from the previous talk, H3 plus ion. It's a cornerstone in all ion chemical networks. You need ion chemistry to get anything going on in these clouds. The neutral rates are too slow to explain the observations, and you have of course ionization by cosmic rays, and then from that you can start building. And this is this very efficient process is the driving force here, because H3 plus, as was mentioned, is likes to donate its proton to whatever it runs into. So I just put one example of such a system here, how to produce water by having just an oxygen and starting with H3 plus. So it's protonated, and then you have a similar process to the one up here, where you split a hydrogen molecule and take one of the hydrogen atoms and release the other one in such a collision. Like this. And this can be repeated. There's a lot of molecular hydrogen around, and you can end up with H3 plus ion, and then you can have then Mats Larsson will come by and make an associated recombination for you and produce water. So this is just one example of production of these molecules in the interstellar medium. And this is what I want to focus on now. Is the electron here, because now is this negative charge always in the form of electrons? But one imagine that the negative charge could be in a different form. And surely in the as was discussed in the previous talk, in diffuse clouds, it's very unlikely to have any negative ions, because they will not be able to survive UV radiation for a very long time. But maybe there will be different environments where negative ions can be formed. And then one can speculate in what can happen. And up until last year, this was all speculations. We know that in sort of the standard scenario where we end these processes by associated recombination, the electrons are assumed to have thermalized to the low temperature of the environment, and this thermalization, of course, takes place in collisions. So they have to collide them many times, and perhaps they can attach to something to form negative ions. But these negative ions, this is kind of a weak argument since nobody saw any negative ions. Now they have been observed, and there have been direct observations of rotational transitions in the centimeter range for these three molecular ions at the moment: C4H minus, C6H minus, and C8H. And this drawing of the molecule here is just me trying to explain to myself why there was only even numbers here, and I realized that if I want to make this a stable structure and to get the bindings right, then it has to look at this. So, and this is probably in a completely different range of the electromagnetic spectrum picture of this molecular cloud that has actually been observed. And this is a star-forming region, so this is interesting, of course, what kind of chemistry can be going on in such regions where new stars and planets can be formed. And these are just the references to these observations. One of them actually is a little bit older than what I said. It's from 2001, but apparently it was not realized that this was actually this anion that was responsible for this observation until this was found again in a later study. And these studies are complicated. These are messy spectra, and it's always just a very careful experiment done alongside with the astronomical observation that allows the determination here. But it's important to, before I go on now, to say that in diffuse clouds and in many environments, it's very unlikely to have negative ions, and the significance of what the free electron can do to the positive ions is the crucial point. But if we are in a region where we have negative ions, then one can think of what significance does this have. Of course, if you have negative ions, they can directly take part in the synthesis. If you want to build up heavier a molecule, then if you have a negative ion as one component in the reaction, then a very easy way to get rid of excess energy is to release this loosely bound electron. And this is an example from the most simple thing one can think of, producing H2. If you have a cloud of, let's say you have to make the H2 from the beginning, so what you start out with is just having hydrogen atoms, and this is the way the first molecules in the universe are expected to be produced. So first you have hydrogen, then you have a very slow process here, which is the radiative attachment of a free electron to hydrogen to form H-. So the anions precedes the molecules historically in the universe. And then the step to produce H2 is to have an associative detachment process, that is H- and H that meet, and the electron is lost, and it's not the electron that is fast, it's the reaction that is fast. And now, of course, if you have anions in the stellar medium, you can have analogous reactions going on, collisions between anions and neutrals that will be very efficient ways to build bigger systems. And this, as far as I know, this is not being taken into account in any models yet. And the other thing one can think about is, of course, that the chain that I showed you before, the example of producing water, you need some recombination mechanism of positive and negative charges to terminate this process. And if you're in a region where you have your electrons have been attached to something, then of course you should think about mutual neutralization in this as a terminating step. So if you're in a region where there's free electrons, then you should do this experiment with firing and the electron cooler that we just saw. And if you have a situation where you have your negative charge as anions, then you want to do a positive and negative ion collision in this tissue machine. So this actually, I skipped that one because this was an experiment that we just heard about, that Max was talking about. And a development now in the field where we belong, the atomic and molecular ion collision experiments, has been to go towards smaller machines, smaller accelerators that are electrostatic rather than magnetic. The main big advantage in the electrostatic device is when you're going to build it, you find out it costs less money, and there could be some other good reasons as well. And this is the first such machine that was built in Aarhus about 10 years ago. There have been 2 more electrostatic rings close in Japan. One of them even has an electron cooler, so they can do similar experiments of the same kind that Max was discussing before with ion-electron recombination. The special thing about the electrostatic ring is that you normally have maybe higher energy, higher mass, molecular ions in them. And now, finally, to our device here, that is Desiree with its 2 rings and all these electrostatic deflectors that I showed you before. And now, for the first time, there's a real picture. So this is as far as we've gotten so far. So this is actually the size of the main box, which will eventually contain the whole machine. And this is made of ordinary steel. It's 4 centimeters thick, just to hold the air pressure. It's kind of big. It's 4.5 meters long, and 2.5 meters across, and 67 centimeters high.
Is there a point of getting such a heavy machine? I mean, from the vacuum point of view, you would of course round the thing and come up with a very thin. But I mean, it doesn't harm that it's heavy.
No, it doesn't harm that it's heavy. It's the problem the day when we're actually transporting it into this building, that it's so big. But I mean, it's not that bad. This piece is the heaviest piece of the machine, and it weighs 2 tons, so that can be handled. And this is what it will eventually look like. We'll have the 2 platforms. It's the laboratory over there in the big building downstairs, with 2 injectors, and it's made in a fancy way so that one can use either injector to inject into either ring here. And those rings can then take both positive and negative ions. They just have to have opposite charges in the 2 rings. What is not identical in the 2 rings is that it's defined which ring will have the heavier particle. And this can be understood like this. If we manage now to merge 2 beams, put them to equal velocity, and then we come here and we separate them, then we see that we have to have a certain field here to get the ions to go into this ring. And then of course the angle of the other ion will depend on the relative mass relative to the mass of the other ion. So then we need some extra deflectors to get back onto the proper orbit. And then in the forward direction here, we have the detection of neutrons. So what's so special about this? First of all, it's a double ring. So we can actually make these merged beams positive and negative ion collisions. Merged beams, this kind of experiment has been done in single pass experiments. But then we have, of course, now the same advantage that we heard about in the previous talk, that if you store a molecular ion for some time, then it will relax to the vibrational ground state. And then we have the advantage of the next point here, that it's a cold system, so that if we wait long enough, then also the molecular ions will be cold. Another thing we gain from having a cold system is that we get a very good vacuum, so we can have a very long storage lifetime. And if one is, there could be different ways to study the reaction of positive and negative ions. You can have, there are actually experiments made in traps where you trap both positive and negative ions at the same time in the same trap and analyze what comes out. But what we have then in the special collision situation is that we have the detailed collision energy control. And then we have the possibility of, with the electrostatic confinement, the possibility of going to very heavy molecules. At a certain level of mass, that you get a faster ion in a small electrostatic machine than you have in a big magnetic machine, because of the trivial fact that the force becomes proportional to the velocity of the magnetic storage. So a point here, which is here shown in the case of ionic electrons, is that if you use merged beams and you have a certain spread of energy, then by moving away from zero velocity, you gain this you gain precision in velocity for a given spread of energy, because of the trivial fact that the energy is proportional to the velocity squared. And this means that in the case of ion electrons, if you take an ion energy corresponding to 1000 eV electrons, then you go away 10 eV to change 25 milli eV, the relative energy of the two particles. And this, of course, is true whether it's ion-electron collision or whether it's ion-ion collisions. So this means that we can go to low relative energies. And the aim is to be able to measure the cross-sectional processes down to 10 milli-electron volt of relative energy. So, what have we done so far? We have made a test DESIREE, which is a double-walled vacuum chamber like DESIREE will be, with cold inner part and a not so cold screen cooled by a cryogenerator. It's the same structure that we use in DESIREE, and we tested that to see that we can get the temperatures that we expect, and we have tested the detectors that we want to use in there. So we put a microchannel plate detector in there and looked at the shape of the pulses as a function of temperature of the whole system. And we found that it's a microchannel plate with a phosphor screen, so that all the information that's taken out from the inside of this big machine will be taken out optically. And this is maybe not so interesting, but this is the main conclusion here is that if we lower the temperature, we see that the pulse type distribution gets distorted. It gets worse and worse. But then when we cool down to the very lowest temperature, for some reason which we don't understand, it gets very nice again. So the main point of this test was to see that the detectors worked. What we're doing right now, also in the small cold chamber, is that we are installing a small electrostatic trap. It's only 17.5 centimeters long. That we cool that down and measure the lifetime of the stored particles as a function of the temperature. Because it turns out that when we go to the low temperatures, we're not able to measure the pressure inside the cold system in any other way. So by doing this test with this test DESIREE, we get some indication of what kind of vacuum we can expect to get in the real DESIREE in the next stage. So I think that I will not say anything about the last part here. So the most important to mention, of course, is that this project is funded by the Swedish Research Council and by the Wallenberg Foundation, and these are the people here involved. And then I would like to thank you for your patience. I feel that I should have stayed home in bed this morning. Okay. Thank you.
Questions?
So your aim in the long run is to analyze heavier molecules, and then could be done before.
Well, there are several different purposes, and we are many different people involved in this project. Several of those people are in the room, and one aspect is to study the process of mutual neutralization in detail for simple small molecular systems, just for the sake of that. But then, of course, there's this astrophysical aspects that I was trying to address here, of the importance of some rates for example, mutual neutralization processes. Now that we know that high negative ions, there are ideas of studying different biomolecular systems. And one key point, of course, is that we are able to address chemical systems than for example, in the firing. But this is not, I mean, it would be a dream to have this machine running and being able to do measurements here and at the same time have the crime ring to do measurements there. It's really different things that we can do. And I think that it's not realistic that we will have the two machines at the same time, unfortunately. But it's not so that we are building this one instead of private. It's not the way to see it. If that was what you...
Now what? No, but you can study heavier molecules in the...
We can study with the electrostatic storage. We don't have the same principle upper mass limit that you have in the magnetic system. I mean, if you choose your injection energy, then any ion, independent of its mass, will need to have the same voltage settings on all the elements. So we don't have that same limitation. If you do that with a magnetic machine and go to more and more heavy systems, then you find that your magnets are not big enough anymore because you need to scale.
You said, or you were giving an indication that negative ion chemistry could be important in the solar medium, in the gas phase. So I understand.
Now I'm speculating.
Yeah, and me too. The question is, we know there have been spectral scans, and you were pointing at mostly the ions which were found in these surveys, the positive ions. Now, from these upper limits in these spectral scans to negative ion concentration, one should perhaps be able to estimate the importance of the negative ion chemistry.
Yeah. I mean,
has this been done, or it's an almost too naive question?
Well, then it makes it even more embarrassing that I cannot answer. But I mean, I didn't mention that, but the abundance of the negative species in the case of these anions that have been detected, relative to the neutral, is 10, 20, 30%. So it's not just a few anions in the cloud. And of course, what one should compare is to get an idea. Of course, is one should get a feeling for the number of negative ions relative to the number of positive ions, because the number of positive ions is also the total number of negatively charged particles around. And,
yeah, I mean, conventionally we're using, say, HCO plus in order to estimate electron density. So
yeah, exactly. But I mean, if you're in a region where you can then find that some molecular species are negatively charged up to 30%, then maybe one can question whether all the negative charges, I mean, whether at least some of the negative charges is not uniform.
I'm just wondering why they haven't been seen in all these spectral scans. They have used telescope time up to death, and then they don't see any negative ions.
Well, they are beginning to see them now.
I think one reason could be that the laboratory spectrum was not that well known. It's an extremely difficult problem to determine the laboratory spectrum of negative ion.
So all these U lines significant fraction of the U lines could be negative.
I don't know. I mean, that's also. But it's interesting that we thought that this could be of importance for negative ions, but when we proposed this machine, nobody had ever seen it. And then last year came these two discoveries of negative ions.
One should also remember that the reaction rates involved in the negative ions are huge compared to any other. Because I mean, essentially it goes as the binding energy of the last electron. So since they are loosely bound, quite often the reaction rates will be very large.
But it's seems to be a contradiction there, because the value would expect to find very, very low abundance of molecules. Tend to be very reactive, the abundance should be very low.
Yeah, but they must be very reactive.
But on the other hand, then, as we heard, the relative ratio is something like 20% for the neutral.
Yes.
There's something tricky there.
Yeah, maybe that. I mean, I don't know this on the quantitative level, but I suppose that these molecules are very few in the first place. So it's 20%, but it's not 20% of a very large fraction of the gas in the town.
No, but still. Okay. More questions? I think we and it's coffee time, yeah.
So these chain molecules are then found in a few specialized regions.
Jo, alltså det här finns det ju folk här som kan mycket mer om jag kan. Varför man ser de just denna serien. Jag har ju mist som mest av vi har spekulerat i ifall det finns negationer här så kunde det vara en intressant aspekt som vi kan titta på med det här. Så vi spekulerar i om det kunde finnas, och då är det förstås väldigt roligt att få reda på det. Men det är ju på den nivån som man...
Ja.
Men det är helt sant att du säger något.
Nej, jag säger inte emot, jag bara undrar. Har de, jag menar... Jag har alltid varit lite skeptisk mot, jag menar, frågan, när vi... Teleskoptid är väldigt dyrt. Både därför att det är många som vill ha det och pengar. Och de här spektrala frekvenserna de tar enorma teleskop. Och jag tycker att det är märkligt att man inte har sett det. Så simpelt var vi frågar. Varför har de missat?
Alltså de som de har identifierat nu, eller de här andra.
Ja, det är det samma personer.
Det är samma personer, och allting är gjort som alltså kombination av laboratoriemätningar och observationer. Alltså,
om de letar specifikt efter dem så kan gå djupare än man bara önskar fuska.
Ja, visst. Ja. Visst.
Jo, alltså precis.
Men vad jag sa det att från